Hi, I'm Katrina Ligett. I'm a computer science professor at the Hebrew University of Jerusalem, and today I'll be speaking with you in praise of flawed mathematical models. I'm really honored to be joining you here today. The FAccT community is really doing crucial work, helping us all become more thoughtful about algorithmic systems and their roles in perpetrating bias, in reducing accountability, and entrenching injustice. And I think really one of the big strengths of this community is its interdisciplinarity and the efforts that are being made here to bridge across different perspectives and different toolkits so that together we can do better and more meaningful work. With that interdisciplinarity in mind, and against this backdrop of strong scrutiny of the all-powerful algorithm, I thought it might be worthwhile to have a chat about what mathematical models can be good for and how I see their place in this endeavor. My perspective on these issues has been shaped and informed by many really terrific colleagues and collaborators, and also by the communities that I've had the good fortune of participating in. Today's talk is really an opinion piece, though, and the opinions are my own. So the starting point for this discussion is that it's clear to me, at least, that we're not going to be able to tech away the problems that are raised by big data and by algorithmic decision making. But it's also clear to me that we won't be able to legislate them away. Progress in this space is going to rely on a diversity of tools from different disciplines and developed with a deep awareness of the affordances and the weaknesses of each working in harmony. So that's really my goal here, to share my perspective on the role and the value of the mathematical toolkit for addressing societal concerns stemming from data and algorithms so that the mathematical toolkit and the overall endeavor can be made maximally impactful. Maybe I'll start by sharing some background on who I am and the forces that have shaped my perspective on these issues. I grew up in my formative academic years in the culture of theoretical computer science, a culture that deeply values rigor, precision, mathematical formalism, and mathematical proof. I came to realize over the course of my studies that the problems that interested me the most were those that were inspired by the real world, and particularly by human behavior and human concerns. One of the areas that I've worked in is at the intersection point between theoretical computer science and game theory, an area where individual incentives and their implications for system-wide behavior are key. My PhD thesis work was on trying to understand how large systems where lots of different individuals interact with and affect one another, so for example, road traffic and internet traffic are prime examples, what happens in these large systems when each individual acts selfishly to optimize their own performance. What happens to the system as a whole, for example, when individuals use, say, standard machine learning algorithms to decide on their strategies? Where a strategy might be something like, which route do I choose to use in going from home to work? Because the decisions that I make as an individual, the decisions you make as an individual, collectively affect traffic for all of us. Now, this theoretical work, well, it looks kind of like this. It might lack a certain visual appeal, and this might not be the language in which you're most comfortable expressing yourself, depending on your background and training. But I'd argue that understanding and having a deep understanding of what characteristics of complex systems can cause them to perform badly when the systems are used by individuals that are each separately optimizing their own performance, that having that kind of an understanding can help us to think about how to do a better job of designing such systems, be they roads or computing systems or systems of voting. I was also fortunate in my early days of graduate school to sort of stumble into the nascent area of differential privacy. This was the early days, shortly after Dwork, Nassim, McSherry, Smith's landmark paper giving the world its first definition of privacy for statistical databases. It comes with really any sort of provable properties. Before differential privacy came along, and honestly, unfortunately, still in practice in many of the places that are handling your data and my data right now as we speak, the sort of the act and practice of protecting privacy really even on very sensitive data, and even as done by the world's experts, was and often is sort of a make your best guess and cross your fingers kind of an affair. Let's, delete this column. This is obviously a bad idea. Okay, we should probably drop names. Maybe, date of birth is too specific. Let's sort of coarsen that to month of birth. Let's try to swap some of these cells around, cross our fingers, and go. And perhaps inevitably, these ad hoc approaches have endless data compromises and heartache. It's been a really interesting experience to have a somewhat front row seat to see this alternative approach, this rigorous mathematical definition of privacy and statistical databases, to see it taking on a very human, very societal problem, and to see how it's developed mathematically, but also how it's been deployed and how those things have evolved over the years and what some of the challenges have been. And because of this background that I have in differential privacy, I'll actually use privacy and differential privacy as running examples throughout this talk. Although I think that some of the concerns that the FAccT community focuses on have some serious differences with privacy and privacy problems, there are a lot of commonalities there, at least from my perspective, in terms of how we can understand the role of mathematical models. I'm also particularly interested in exploring the power and limitations of mathematical models with you because of my deep respect for and interest in cross-disciplinary dialogue. I view myself in many of my research contexts as a translator of sorts. As I said, I'm a computer scientist, but in my first faculty job at Caltech, I not only started publishing with economists, I was actually 50% an economics faculty member. And thanks to Caltech's relatively flat organizational structure, this meant that I was a direct colleague to all of the social scientists there, the political scientists, the finance faculty, and more. At the Hebrew University, I'm a member of the Fetterman Center for the Study of Rationality, which delightfully puts me in direct contact with faculty in math, statistics, economics, psychology, law, biology, business, sociology. I also head the program here at the Hebrew University on Internet and Society, which is a cross-disciplinary undergraduate degree program. And most recently, jointly with Kobe Nassim at Georgetown University, I'm also co-leading a growing research collaboration on the subject of data cooperatives. And that project really crucially relies on cross-disciplinary work. Through it, for example, I'm currently working with two really wonderful postdocs who both received their PhDs in law. Okay, so what do I mean when I say I come to speak in praise of mathematical models? What do I even mean by a mathematical model anyway? So really, I just mean a definition that precisely states any underlying assumptions and precisely states what satisfies, and by implication, what doesn't satisfy the definition. And we typically use mathematical notation in the definition or natural words that have been defined to have precise mathematical meaning. This formality means that it's possible to check whether or not something satisfies the definition, although it's not necessarily easy to check, but that there's no room for disagreement. An example might be the definition of differential privacy, or of a protocol for a group of people to come to a consensus, or a definition of a particular fairness criterion. Now, you might not say that differential privacy is a perfect match for your own personal intuitive notion of privacy, or for what you've read on papers of philosophy of privacy. You might not think that this particular protocol for coming to consensus is a good one to follow at your next faculty meeting. And you might, for example, think that ensuring, say, this particular fairness criterion in an app that rates, say, job applicants would do more harm than good. That's okay. I'd like to argue that the formalism of these definitions is still helpful. So the most important point that I want to make here today is about the role of mathematical models of social phenomena. And my claim is that the role of mathematical models is not to determine what should be done, but to illuminate fundamental tensions and possibilities. A mathematical model or a definition doesn't contain a should. It doesn't really contain a good or a must or a right For those, we need humans. We need ethicists, we need policymakers, philosophers, ordinary people setting their priorities in life. But math can tell us that, say, under some assumption X, algorithm A is more accurate than algorithm B for some accuracy criterion Z. But does that mean it's better for society to run algorithm A than to run algorithm B? No, not necessarily. Is it better for me? No, not necessarily. Maybe algorithm A is more accurate, but say less fair, or more energy intensive to run, or more privacy harmful. Math can highlight these tensions, but it doesn't tell us what to prioritize. Now, there's sort of a tricky thing here. I don't mean to imply that mathematical notions are devoid of values or of ethical meaning. On the contrary, an algorithm that prioritizes accuracy over differential privacy is making a choice, and that choice is surely ethically loaded and complex. But the possibility or the existence of that algorithm doesn't tell us that it's the right or the wrong one to run. What mathematical models are supremely good at doing for us is showing us what's possible. That it's possible to achieve this level of, say, this fairness notion at the same time as this level of this accuracy notion. Equally importantly, they're good at showing us what's impossible. Say, under the following assumptions, it's not possible for any algorithm at any sort to guarantee this level of differential privacy alongside that level of accuracy. And this, they show us how we must trade off between various desiderata, regardless of whether it's an algorithm or a human that's making the decisions. Now, once you have two formally defined objectives, things that you would like to have as a result of your algorithm or your model, say privacy and accuracy, and a formal setting in which to study them, you're now in a position to map the trade-offs between those two objectives. You can do this sort of plot that I have here on this graph for sort of at least two different purposes. One is you can either plot the trade-offs between, say, privacy and accuracy achieved by a particular algorithm. Here I have this algorithm, I can tune its parameter, and I can see at this level of privacy it achieves that level of accuracy. Let me try a different level of privacy. Oh, okay, now it achieves that level of accuracy. Or you can plot the feasible trade-offs that are provably achievable by any algorithm. Now, the dots in this plot, both the gray ones and the red ones, all show possible trade-offs between privacy and accuracy. And the red dots are the so-called Pareto frontier. Those are the best trade-offs. Notice that, for example, dot K is not on the Pareto frontier since it's dominated by dot D. So that means that D manages to get both more of item 1, say privacy, than K does, and simultaneously it manages to get more of item 2, say accuracy, than K does. Similarly, dot E dominates dot N. And now once you have a plot of the Pareto frontier that's achievable by any algorithm and not just by some particular algorithm, it tells you about what's possible. It tells you no algorithm at all, no matter how clever, can achieve a privacy accuracy combination that's above or to the right of the red curve. Now, there's some fundamental trade-offs that need to be made between privacy and accuracy, and it's an important conversation. And this is a conversation we couldn't even begin to have unless we defined privacy and accuracy formally and proved something about them. Now, of course, if you've modeled privacy or accuracy in a way that doesn't match the meaning you think they should have, or if your assumptions are wrong, or if you also care about some third quantity like computational efficiency, but you say failed to even model it, then you're going to have to deal with those issues. But really, I said before that the role of mathematical models is not to determine what should be done, but how to illuminate fundamental tensions and possibilities. And the flip side of this is that once you know about those tensions and possibilities, you know what decisions to be made. And this can help us focus attention on where we need inputs from other fields beyond mathematics. once you know that there's a fundamental tension between, say, privacy and accuracy, you know that any actions that will be taken, any algorithm that you run, any human decision maker who makes a choice will be implicitly selecting a privacy accuracy trade-off point. And that makes it crystal clear that you need an input that math simply doesn't give you. You need guidance on how privacy should be traded off against accuracy in this particular setting that we're studying today. Say, providing researchers with data on coronavirus vaccine efficacy. Math alone won't tell you whether it's worthwhile to society to, say, give a slightly worse differential privacy guarantee, say move from a parameter of 0.2 to a parameter of 0.5 in order to gain a few percentage points in accuracy. But if that's the necessary trade-off, now we know, thanks to the model, we as a society need to decide who should decide this trade-off, because it has to be decided. Who should decide it for whom? What mechanism should they use to make their decision? And we'll need those decision makers to understand what they're trading off against what. Now, of course, mathematical models are always imperfect models of reality. They make assumptions, and those assumptions may not hold up in the setting that you care about. But by making those assumptions formal and explicit, it becomes a well-defined and potentially actually answerable question how well the model applies to your setting. So for example, once I know that a particular model assumes that people are, say, risk neutral, meaning, for example, that they'd be indifferent between getting an opportunity to be just given $10 versus an opportunity where half the time they get $30 and half the time they actually owe $10, we can start to evaluate how well does this assumption hold for real people in the setting that we care about. We can also start to assess how robust the conclusions are to, say, weakening the assumptions of the model. And this is crucial to making progress towards models with more realistic or weaker assumptions. But for all of this, you need to be able to lay out your assumptions explicitly. Once you're reasonably satisfied with the assumptions going into a model, one of the greatest advantages is that a rigorously mathematically defined notion can be used as the basis for making rigorous mathematical claims. But don't be misled by the word claims. Mathematical claims are not a matter of opinion. They are, once you accept the assumptions and the premises on which they're based, they're facts. So when I say that the privacy guarantee given by a differentially private algorithm can't be degraded or destroyed by some clever attacker who comes along, looks at the results of the algorithm, post-processes them in some interesting way, combines them with some super powerful outside knowledge, no matter what that attacker does, they can't degrade the differential privacy guarantee. When I say that, I'm not basing that on me having tried and failed to break the algorithm. I'm not basing it on just hoping the attackers won't be more clever than I am. I'm making a formal mathematical statement. And when you can have a formal mathematical statement of this sort, that really lets you sleep well at night. You don't need to hope that the attackers are going to be only using a particular toolkit and not some other one, or that they'll only be so clever or only have so much computational power, or you hope you thought of all the possibilities and all of the gaps to close. You have a proof. Of course, there's still the potential to have gaps between mathematical models and between realities. So for example, the programmer that's implementing my differentially private algorithm, or say the programming language it's implemented in, might introduce errors that cause the implementation to no longer be actually differentially private. But this lets us narrow the focus of our concern to implementation issues, and it lets us set aside the nightmares of ad hoc solutions that crumble under pressure. I don't want to overemphasize this because I think mathematical models have a real and very meaningful role even when they don't make testable predictions. But because of the precise nature of their claims, mathematical models do sometimes make falsifiable predictions. By that, I just mean that they make predictions about future or unseen data or observations, and that when you line up that future information, that evidence, that data with the predictions, you can see how well they match up. And you can use that as a tool to help evaluate the suitability of the model for the setting. And that can be quite nice. But even more than this, I really want to emphasize that models and theorems about them together represent the gradual accumulation of more and more understanding, of more and more knowledge. And because this knowledge and this progress is represented in a consistent formal language, it provides a firm foundation on which additional models and additional theorems and additional insights and understanding can be built. And this accumulation of our collective understanding has historically, over and over, led both to really exciting mathematical insights, but also to practical consequences that the researchers who were involved in laying the early bricks of the foundation simply could not have anticipated. We wouldn't have, for example, modern cryptography if not for investment in fundamental mathematics that at the time looked honestly, somewhat obscure, upon which researchers introduced new models that honestly at the time looked somewhat strange. But this formalism of mathematics and this sort of consistency that this formalism enables allows us to build up these structures and to build up our level of sophistication and understanding. Now, of course, it's not all roses. As we know, the conclusions of a mathematical model, of course, rely on the alignment of the model itself with human intent, rely on the model's assumptions, and those being valid assumptions and sufficient assumptions, rely on any data that the model has been fed. And if any of these things go wrong, then really mathematical models can they can be misused, they can be misinterpreted. This is not to say that once you have some math, it's all easy and all problems are solved. Far from it. So let me talk briefly about some of these ways in which mathematical models can go wrong. So the first is about sort of definitions and goals. So if you mathematically define, say, the notion of equal opportunity one way, it of course that doesn't mean that the math automatically captures what that phrase means to humans in some particular context. In fact, it almost certainly doesn't match perfectly. So careful academic work really needs to focus on this challenging task of bridging between mathematical notions and legal and ethical notions. And I really encourage this community to take on this task. And I see some work in this vein already happening, but more and more, I think this is really crucial, this bridging and translation type of work. Relatedly, if you mathematically seek to optimize for accuracy, but really what you wanted from your algorithm was, say, to optimize for accuracy, but subject to some constraints on privacy, fairness, energy efficiency, a little bit of this, a little bit of that, it's no wonder that you'll be disappointed by the results. The results will optimize for accuracy. They may sacrifice privacy, fairness, energy efficiency, and they may do so horribly. That's not the fault of formalism, but it's an important point to pay attention to, that mathematics is very literal. And if you don't say what you mean, you'll get something other than what you mean. And all those assumptions that we talked about before, we really do need to scrutinize them. There's a joke that the physicist starts her work, first we assume a spherical cow, and continues on from there. And we need to be skeptical of that spherical cow and what's lost in assuming it. To what extent is this an acceptable simplification of the real world? How sensitive are our conclusions to making this assumption? What if I were to relax this assumption a little bit? What would happen? Can I think of important cases where this assumption is grossly violated? Because we don't want to just model sort of the average case, but in many situations, we really care about the extremes, the outliers. And so it's important to be critical of assumptions with that in mind. And of course, if you pour garbage into your models, or if you intentionally seek to deceive yourself or others with your results, or you abuse statistics in your pursuit of something that looks interesting and overfit like crazy, there's a lot of harm that can come. You can do things that look very plausible with math, but actually don't stand to scrutiny. And I think there's a lot of risk there, and there's a lot of opportunity for intentional and unintentional errors and confusions. But perhaps the biggest cautionary tale that I want to draw attention to here is that mathematical models can serve as a fig leaf, hiding or providing an excuse for bad behavior. And I think we need to be very, very careful, particularly when we're talking about mathematical models of social phenomena, mathematical models of issues where there's real potential for harm to individuals and harm to groups and harm to society. We need to be very, very careful not to give an algorithm a pass just because it has some nice mathematical properties, but rather we need to think deeply about whether or not this algorithm meets all of the criteria that we as a society set for it to be considered right, for it to be considered just, for it to be considered worth the costs and the trade-offs that it comes with. So mathematical formalism gives us language to make progress towards addressing those questions, but we have to ask the questions. And it's important to keep in mind, you can throw in all the buzzwords you want, secure, multi-party, differentially private algorithm. If it's an implementation of a discriminatory algorithm, it can still be discriminatory. A differentially private algorithm that gives a differential privacy guarantee where the parameter is a million, it's a knob you turn in order to say how good the privacy is. Well, it's technically, in some sense, differentially private, but it's not meaningfully so. And if deployment of differential privacy is providing cover for companies to gather and use more of our data, maybe this doesn't get us to a better equilibrium as a society. And this is, I think, really crucial. We must always do our best to consider the broader picture, the context in which our algorithms are deployed, the equilibrium effects. What else will change once I deploy this, once I make this decision? What are the downstream impacts? What are the feedback loops of any decision? And that's hard work to do, but I'd claim that it wouldn't hurt to model these aspects mathematically as well. That rigorous approach, for all its flaws, does have a lot going for it, for its ability to illuminate fundamental tensions, possibilities, for its ability to focus attention on inputs that are needed from other fields, to make its assumptions explicit, to come with provable guarantees, to sometimes make testable predictions, and to make progress that's built on a firm foundation. So I think it's really crucial that even though we'll never have a perfect model of, say, how bias enters a decision-making process, that attempt to model the process is still valuable. It's really valuable that we critique the model. It's valuable that we examine its assumptions, that we explore its implications, its predictions, that we see what tensions and possibilities it highlights, and we use it as the basis for making further discoveries and progress. The algorithmic decision maker, I think, is a convenient scapegoat in some cases, but we need that formal language of the algorithm if we're going to set standards, if we're going to audit practices, if we're going to detect injustices, whether decisions are being made by a machine or by humans. So with that, I share my praise of flawed mathematical models. Thank you for taking the time to listen, and I look forward to our discussion and to your questions.
All right, I think we're live. Thank you, Katrina, for that talk. That was awesome. And before we start, I'd just like to remind our audience that you can post your questions in Slido, and many people have. And if and there's closed captioning during the live session as well, and there's a link you can click on for that. So let's just get into the questions. There's a bunch of questions in the chat, and I'm going to try and sort of distill out some themes from some of these questions. And I think the first theme that I want to ask you about really is the idea of a limit, right? The limits on mathematical model. You talk a lot about the value of models. We know that maybe all models are flawed, but they're often useful, to take Box's quote. But I think, as we've seen happens in other domains that use mathematical modeling to model society, things like econ and others, there's a fundamental question you then have to ask is, to what extent is it even possible? Is a mathematical language even the right language, or even an accessible language to access things about people? I'm thinking of issues of power dynamics, for example, in games. I'm thinking of issues of fundamentally contested notions, things like fairness and bias that look very different from who's asking the question. I'm thinking of context, of course. Given all of that, right? And then this goes to sort of a little bit of what Christian's question is also about, right? Do we run the risk with mathematical models of focusing our attention on things for which mathematical models make sense versus things for which we care?
Great, thank you. I just want to open by saying thank you, Suresh, for being with us, and it's an honor to share the virtual stage with you, and thanks everyone for the questions so far. So great question. Yes, I absolutely think that those of us who enjoy mathematically modeling sort of social phenomena, absolutely, we direct our attention to the places where we think we can make progress. We start simple, we make terrible simplifying assumptions, we pay attention to the aspects of the problem where we think we have some hope of getting a grip. Absolutely. That certainly changes the focus, it certainly changes where we make progress, it certainly changes where there is sort of attention being paid by this community. And that's something to be aware of. I'm not sure that there's anything else that we can do about it other than to continually be aware that we have forces that are guiding where our attention and our efforts are going, and that we continually try to engage with communities that have other toolkits for engaging with other aspects of the problem. But it's only by starting modest, by starting small, by starting with flawed models that don't capture everything, that we're going to make any progress on the mathematical modeling side. We have to start somewhere. So I don't think the limitations are a reason not to start, but we continually have to be aware that, yes, our attention's being drawn somewhere in particular, and it's not always to the most important or impactful aspects of the problem. That's absolutely true. There was something else. I mean, there were a bunch of threads together in that question, so I won't hit all of them. But another one that you mentioned is sort of the problems with mathematical modeling, of course, aren't unique to fairness or the FACT concerns. And absolutely, we see similar issues discussed in the context of, as you mentioned, economics. And I think, yes, we can also learn from some of the caveats and problems that we've seen from mathematical modeling in other communities. And certainly you can see mathematical models abused, and it's embarrassing, it's outrageous. You see claims made by prominent modelers and theorists claiming that they can predict or understand human phenomena where their models are clearly unable to make meaningful predictions or claims. So yes, we need to have caution. Humans are complicated. Humans are unpredictable. They bring really challenging aspects to the phenomena that we model, in particular things like correlated randomness, herding behavior, and also there are these concerns that there's something human or humane that's lost in this reductionist act of deciding this makes it in the model, this doesn't make it in the model. I know how to say this in math, so this makes the cut. But again, I don't think it's a reason not to model, but it's certainly a reason to not only model. And I think there's a question that alludes to this in the Slido. I think it's a beautiful question that I don't have a good answer to, but I think we should be devoting serious effort to modeling what we lose by modeling, by understanding in as rigorous a fashion as we can what's not making the cut and why, and is that fundamental, or are there ways in which we can hope that we'll expand our horizons?
I want to keep going on with this, but I think there's another thread of sentiment that I wanted to ask you about that's also in the Slido. That is sort of about the sociology of doing mathematical modeling, right? And so, and then I think one version of that question would be, you are being extremely cautious, and you're fence posting your claims about mathematical modeling in a way that's very appropriate. And I think anyone listening to you will recognize that you're not making broad claims. However, the truth is that math tends to have this kind of power to it. It has this sort of allure of, sort of objectivity with square quotes. Math is intimidating to people, and therefore people feel unable to respond to it and take it as gospel. It has this sort of power. And I think there are two parts to this. One part of this is that when facing outwards, to policymakers, to lawyers, to people in outside society, where maybe they don't have the same way of thinking about mathematical models the way you do, it has a sort of force that is more powerful than it should have, given all the caveats you said. That's one side of it. The other side of it internally, and as you talked about this in your talk about the sort of firm foundation, because it creates what looks like a firm foundation of mathematical reasoning, it tempts people, especially researchers in the area, to jump on a particular model and build huge edifices of reasoning on top of it, without necessarily being willing to contest the basic premises on which that model built. So these two ways in which the sociology of doing mathematics kind of changes its perception beyond what you are willing to concede. What do you think? How do you address that? Because you can't ignore that this happens.
Absolutely, you're completely right. I don't think I have a bulletproof answer there, but I think for part one, this concern that math has this shine to it, and therefore you throw some equations on a slide and then you can get away with anything. I think one way to try to address this is for anyone who's doing any sort of mathematical modeling of social phenomena to view a core part of their responsibility and mission to be publicly critical and vocal about the limitations, to be speaking to the impossibilities, to be speaking directly to the tensions, and to be trying to use this mathematical language not just to sort of conjure up a dream where we solve all the problems, but to be using this mathematical language to talk about the limitations. Of course, everybody likes a positive story, and it's harder to get attention, I think, when you come as the bearer of bad news. So I think we should all view that responsibility as something that we need to continually return to. It's not a bulletproof solution, though, and I think each of us individually and each of these communities that do this kind of work will continually grapple with misuses of their work and public statements that don't accord with mathematical understanding. I think it's going to be an ongoing struggle. To the second part, I like this sort of discussion of mathematics and mathematical modeling as more of a human endeavor, because it is. And I think that's really important to acknowledge in many, many ways, to understand its powers, to understand its limitations, and to understand how do you build an environment in order for it to be maximally successful and impactful and useful. And it's a tricky thing. So you pointed to this phenomenon where somebody comes up with a new cool sounding definition that has fun mathematical properties, and next thing you know, a dozen graduate students are writing papers that exploit these interesting properties and port that notion into a dozen new settings. And yes, this happens, and it sometimes means that we see a dozen papers in a year about something that nobody's going to care about in 5 years. It happens a lot. I actually don't think that's a disaster. I mean, it's a shame for the student in some sense that paper is not going to be, the most important thing they've ever written, but that's also okay. In the slides, where I had that image of the brick wall that gave a very sort of neat and clean depiction of the development and evolution of mathematical models and our understanding. But the reality is much, much messier. And like you said, mathematics is this human endeavor, and it takes time to mature, and it's not going to have a clean, pristine evolution. It needs dead ends. It needs overinvestment in bad ideas. It needs additional toy models that fail to model crucial components of the underlying problem. And we need an environment in which that kind of exploration is safe and encouraged. We need to really not expect our models, at least our initial models, to model reality well in all ways. But we do, of course, need to have some degree of dialogue with the reality so that the models don't get dragged off permanently into unproductive directions. And I think there's a delicate dance to be done there, where you need to give the math its space to grow and explore and thrive, but you don't want it to become divorced from the phenomena it's trying to understand.
Right. And I think, I mean, that makes sense. And this issue of a deeper engagement, I think, is what you're advocating for between the modeling work and what's happening out in the world. And I think, which is, again, different from a lot of, say, your papers at a sort of theoretical computer science conference or something like that, where they would not necessarily be doing that engagement, but you're saying that is important, and I agree. Another issue that comes up really is, and I think, so I'm going to channel two different people. One person is the non sort of mathematically adept individual who's working in this space, who is hearing claims coming from sort of someone who's proficiently waving their math sword and has listened to your talk and wants to know how to push back on them and doesn't know how. So that's one person. And the other person is, say, maybe a graduate student in theory, let's say, who wants to work in this area, has listened to your talk and is conscious now of the limits and how to be cautious about taking their models too seriously. What is a way to test? What is a thing you can use to test as either of these people, where the limits are and probe those limits? What kinds of questions would you recommend people ask to probe the limits when someone comes with these broad claims about something to enable more skepticism?
That's a great question. I mean, of course, you always ask about the assumptions. You always ask about, really what is the setting that you have in mind when you propose this model. And I always find it helpful to get sort of painfully specific in some of these discussions. Like, let's come up with a very concrete situation and try to nail the model to something really very concrete so that we can really understand specifically, what is this X and what is this Y and how does that really line up? I think that's a great question. What are the right questions to ask to have this sort of appropriate level of skepticism and sort of how do you push the models forward so that they can make more and more progress? I guess I think part of what you do is this sort of, like I said, a dance of forward and back. So you dive into the model, take it as it is for a period of time, and then you step back and you try to ask yourself, okay, so what have we learned in that dive in? Does it tell us anything that we should be seeing in the real world? Can we match it up with reality? Does it suggest that maybe something is missing? So somehow, it's not a specific question, but somehow this awareness that sometimes you're in the phase of diving in and sometimes you're in the phase of stepping back and reflecting. And I think having both of those is important.
Do you have any, I mean, you've worked in a number of areas that sort of sit in this bridge. You've worked in privacy, you've worked in economics. So you have a sense, right, of that boundary between the interface between the mathematical and the people, right? Are there any, without maybe shaming anyone in particular, but are there any examples that come to mind maybe of, just to make this a bit more fun, of places where, this did not work very as well as one would have liked, right? This thing was, maybe the best thing to do would have been just to abandon the model itself because it was not working. Are there any things just examples you can give us here?
I should probably not shame anyone, like you said.
Or you could, that's fine too.
But I mean, all of us who do this work have worked at various points on models that ended up not being all that interesting, on models that ended up actually not really capturing what they were hoping to. The experience, the sort of path by which you arrive at a model is sort of a weird one. And there are a bunch of different ways you get there. But sometimes I feel like there's this thing going on in the real world. I think there's a mathematical story that can go along with this. Let me try to pare this down and cut out as many details as I can so I can get to the point where I really capture the core phenomenon here. So this is something that happened to me, over the past couple of years, where I felt like there ought to be a nice story to tell about how there could be a productive interaction between somebody who's setting objectives or criteria and somebody who's trying to game those objectives. And if there's an interaction between the two sides, maybe that could actually be kind of useful, because when somebody games my criteria, I later see that they actually failed to perform well. And so I therefore learn to improve my criteria. And therefore, now the next person who comes along has to face better criteria. Maybe they managed to game it, but if they do, I learned something about how my criteria were bad and they get better. So I felt like there's got to be a story like this. And so then I went around talking to people and saying, okay, where might this be happening? What's the core thing that's going on here? When I say they're interacting, what does that mean? What is the method of the interaction? How do you model that? And there's probably 100 different ways you could model it. So there's some search for, how do you isolate the real thing that's going on here? And so I think that's, for somebody who doesn't engage in this kind of activity, I think it's interesting to try to get some view into how it happens. And I think it really exposes this. Again, it's a very, very human, very alive kind of a process. It's not that, somebody hands me a description and I translate it, character by character into mathematics. There's a search and there's a process there. And I think it's, you don't always end up with the most interesting model, or you don't always end up with a good model. And sometimes you end up with really boring results. I mean, sometimes you model something and it turns out it's just not that interesting, the aspect that you captured.
And I think that's a good point, right? That the incentives for theoreticians who want to model phenomenon involve interestingness, mathematical depth, and sort of a certain amount of surprise or counterintuitiveness, none of which may necessarily be relevant to the problem at hand. And often may distract people in other ways. And I think it's good for people who engage with formalizers or people who work with models to realize that sometimes there are shiny things that, and I'll say we here because I've done this as well, get distracted by, that, sometimes we need to be reeled back in. It's okay, that was shiny, but that's not really relevant to what we're doing here. So even if it's boring, it's okay. And I think that's good to keep in mind, I think, for that. Sorry, I'm reading a question here. So it seems to me that a lot of the fence posting around the use of models, and I say fence posting in the caution, involves validating assumptions and being very ruthlessly clear about assumptions, pulling them out even if they're implicit, even assumptions about, oh, we can model this attribute this way is an assumption, and we have to pull these things out very clearly. And as long as you can make those assumptions extremely ruthlessly clear, you have a better sense of the extent and scope and validity of the model. But of course, a lot of assumptions are not sort of binary, testable, not testable. They're kind of fuzzy. It's not always clear. And I've always wondered about, is there a sense in which you can talk about sort of the assumption stability of a model, right? So I have this model, I have these assumptions, I make these claims, but maybe one assumption got tweaked a teeny bit, and then because of the way it fed into the model, the whole result fell apart. Or maybe another case, no, it didn't actually fall apart. It kind of gracefully degraded as the assumption validity degraded. I don't see much of that in the discourse. I don't know if you've seen it, or if there are thoughts on how you might go about doing that.
I think that's a really beautiful direction for exploration. I mean, so absolutely robustness more broadly and generally is a mathematical topic that has gotten historically and is currently getting a lot of attention in various sort of subdisciplines of computer science, math, statistics. Sort of this question of formally, what does it mean to sort of tweak something, and formally, what does it mean for the impact of that tweak to be not too crazy big? And we have lots of mathematical language for talking about that. But you're right, I haven't seen that often explicitly sort of deployed in the context of checking assumption robustness in modeling. And I would love to see some work that tries to push that forward, because I think it's extremely valuable. It's something that if you've ever sort of tried to do some, back of the envelope, coronavirus, armchair epidemiology,
no one's ever done that.
Nobody has ever done something like that. You have to do that. You come up with your little toy model, and then you have your list of, here are the 100 assumptions I made, and here are the, all the simplifying things I did in order to make this. And then you say, okay, well, what if this one we're not true? Or hey, what if this parameter were actually 0.3 instead of 0.5? How much is it going to matter? And you play around with it a little bit, but it would be great to have more discussion about how we can do that in a more robust and rigorous fashion.
Yeah, it also came to mind because you mentioned this sort of in your talk, a distinction between sort of what you can prove theoretically and then focus on implementation. I'm not sure I agree with you that boundary is as clean as that. Often the implementation corrupts maybe what you thought you were proving because of that interaction between the choices you made. And I think that's where assumption stability seems to come into play as well, right? If you made some choice in implementation that seems innocuous, but is actually not, it's because your model was fragile enough that choice of implementation detail invalidated the claims of the model. And it seems like that there's not enough transparency around that communication, I guess, between the theory, so to speak, and the implementation. And that's where it came to mind. Continuing on, looking at some of the questions, I'm trying to distill out. I mean, let me see here. One question, from your side, do you feel that, well, maybe you do because of all these questions, but do you feel that there is a certain level of skepticism that is maybe misplaced about mathematics? I mean, of course, that's what your talk is about, but also I'm saying, is there a specific kind of way of thinking about mathematical models that you would particularly like to push back on, for example? So that you think is just not quite,
one of the things that I'm trying to do in this conversation is to try to emphasize the relative strengths and weaknesses of the mathematical modeling toolkit, because I sort of view this whole FAccT endeavor as a bunch of us are sort of descending on a problem space armed with various tools. And unless we can have a conversation about what my tools are particularly better or worse for, and what your tools are particularly better or worse for, and how they might work together on this problem, I think we're going to run into a lot of misunderstandings and problems and wasted effort and limitations to our collaborations. And so I do feel that sometimes there's been underappreciation of the value of this sort of rigor of the formal statements, of the provable consequences. And it's easy to discredit a mathematical model because they're always flawed. I mean, they always imperfectly capture reality. But I would like to encourage people to try to look for the value in the formalization, even if the value is, it allowed me to point precisely to the place where it's flawed, because that's super valuable.
Yeah, and there was this, of course, very nice paper from last year at FAccT by Abebe et al. Talking about the roles for computing research in this field. And I think that's one of the messages that they had there, that the ability to precisely articulate limits is also a value that comes from this. So I think that point is very well taken. We're we've got a few more minutes to go, and I'm going to continue the questions, but I just want to mention to people that you can continue this conversation in Circle, as many of you have been doing, and there's a specific place for this keynote to continue discussion, and I encourage you to do that. We're not done here, but just before we get cut off, I just want to mention that point. Is there a thing you would say to theoreticians, especially junior theoreticians, grad students, people starting out in this area, advice you'd give them to sort of fight the kind of math is authoritative culture, kind of sort of how would you advise them on how to be cautious? Because they have to sell their papers, they have to sort of market, they have all the pressures of marketing itself, and we've seen this in ML a lot, right? The pressure to sort of maybe overpromise and underdeliver a little bit in how we sort of write our papers is there everywhere. I mean, a lot of career concern. What would you how would you tell people to communicate and message about the theory work they're doing in this space in a way that's, would make you happy and would make the audience
happy? I'm not sure this is so much messaging, but in terms of sort of shaping your worldview so that you can avoid getting sucked into a theory bubble, I think it's about having a broader conversation. So find yourself conversation partners who care about the same kinds of problems that you do, but come with a very different perspective. They're going to be incredibly critical of the approach that you take, and rightly so. But you have to do this dance forward and back. So if you spend all of your time in that conversation, you'll never model anything and you'll never prove anything. So you have to at some point say, yes, it has limitations. I want to go forward and explore it in the context of those limitations. And then you do the dance back. So I think it's about finding conversation partners.
I'll give you the last word. Any last words for us?
I hope this is an ongoing conversation for this community. Thank you for facilitating it. Thank you, everybody who participated. I don't think there are last words here. I hope it's ongoing.
First words and ongoing. On that note, I think I really would like to thank Professor Ligett for being with us today and sharing this. I think this is a very useful insight and very useful perspective to have. And as you can see, there's a lot of discussion about this. Please continue the conversation on Circle. There's clearly a lot more to say. And I apologize for all the people whose questions I could not get to. And hopefully we can continue this in other places all over the web and ongoing next year and in future years of this conference. So thank you very much.